And thank you very much, Jim, for inviting me. And it's a pleasure to be talking at this meeting in honour of you, Bertel. It's really wonderful. I guess most of us know Jim as a biochemist who loves his PS2. But of course, here in Singapore, you're part of the Department of Materials Science and Engineering. And the activity here is not actually on PS2, it's on trying to do something useful, or maybe something useful, in terms of sustainable fuels.
The way you look at things.
So what I'm going to do today is to talk a little bit about some of the work we're doing at Imperial, looking at, as Jim says, rust, at photoelectrodes, which may be interesting for trying to split water into hydrogen and oxygen. But I'm going to be keeping on the theme of kinetics. So I'm following Jasper in the sense of trying to understand timescales, but I'm going to be slowing down a bit. We heard about picoseconds and femtoseconds just now. I'm going to be talking about milliseconds and seconds, because I'm going to be focusing on the timescales of catalysis. I should at the outset say that I should apologise that I like my kinetics, but I don't understand my catalysis, and I'm going to be talking about catalysis, and so I hope I don't say too many stupid things about the catalysis as I go along. So what I'm going to be talking about is how we can measure kinetics of water oxidation on both photoelectrodes and indeed on electrodes for water oxidation. And then think about, and trying to use the language of kinetics in the way which we think about kinetics in photosynthesis, trying to avoid some of the nomenclature of the funny rate constants and things you come across when electrochemists talk about kinetics. But I'm going to be talking about heterogeneous kinetics on poorly defined materials, and trying to get some hard numbers on those sorts of relatively poorly defined inhomogeneous systems, and make some analogies as I go along to PS2. So when we talk about kinetics, then of course we're very used to the idea of timescales of the different steps of the S-state cycle. And the idea you've got a rate determining step going from S3 to S4 for a millisecond and all this sort of thing. And we know all those sorts of numbers. What I'm going to try and do is measure similar sorts of numbers, but for water oxidation. Sometimes we do it in molecular systems. This isn't work we did with Tony Levett, but I'm going to focus on heterogeneous systems. I'm going to be looking at timescales of water oxidation on hematite. Here these are the nanostructured cauliflowers of hematite from Michael Gratzel, or in this case on iron oxyhydroxide, an interesting electrocatalyst for water oxidation. And I'm going to be trying to measure things like time constant and turnover frequencies. And as you'll see, one of the things I'm really going to focus on is how those time constants and frequencies depend upon the degree of oxidation of a material. Well, of course, we've heard a lot in this meeting about mechanism. And here's Jim's favourite mechanism for PS2. This is a mechanism from Tony for a molecular catalyst, and that's a mechanism from Heinz Frey for a cobalt catalyst. And I'll say a little bit as we go along about the details of mechanism of water oxidation on some of these oxide surfaces and how they may be similar or not similar to PS2. But I'm not going to talk too much about the mechanisms, because that's not my expertise. I'm in some ways thinking more simply that when you think about PS2, or if, in this case, a conceptual molecular artificial photosystem, then you have the idea that you absorb a photon, and each time you absorb a photon, you separate charge, and you ratchet up one step in the water oxidation catalysis. You go from S1 to S2 to S3 to S4 in a fairly linear sense that one photon causes one oxidation. When we go to a material, then it's more challenging, because you no longer have one charge separation site and one catalytic site. You have a film of charge separation material coupled to some catalytic surface. And therefore, you have the idea that you can have many photons involved in driving a catalytic surface, and you don't step through the redox states of S1, S2, S3. You increasingly oxidize a surface, and as you oxidize the surface, you can drive towards states which may drive water oxidation. And so you have some idea of a continuous oxidation of a catalytic surface, where holes, as I think of it, because I come from the language of physics, oxidations can move between catalytic sites on a surface, and we have to understand how that interface works. Essentially, it's the idea, if you coupled all those manganese clusters in PS2 into a single unit, so that when you oxidize one element, one cluster, if you oxidize, you can move to the next cluster. And how do we think about that, and what's the impact of that on how we think about water oxidation? And that'll be one of the main themes of what I'll be talking about today. In general, what we do in my group is we do transient spectroscopies, and so typically we have some sort of laser or something which excites a sample, ideally under conditions of operation, so that's in a photoelectrochemical cell with light shining on it, and we measure the carriers by their optical absorbance. And I'm going to focus entirely on the holes, because they're the ones which drive the water oxidation. And so we monitor the lifetimes and yields of those holes optically under conditions of water oxidation. There are many things we can measure in such photoelectrodes, and we can measure the lifetimes of carriers and all this sort of thing. I'm going to focus almost entirely on what are the timescales of water oxidation, what are the rate constants for those holes reacting on the surface. Just before doing that, then of course, this is just to illustrate that just as in PS2, there's a challenge between the short lifetime of a chlorophyll excited state and in the nanosecond timescale and the millisecond a second timescale of water oxidation catalysis. Essentially, it's the same challenge in these photoelectrodes and the same timescales. And so this is the lifetimes of excitations in different oxides. That's hematite, that's titania. Titania's got about 3 orders of magnitude longer lifetime than hematite. But it's picoseconds and nanoseconds. If you want to drive catalysis, then of course picoseconds and nanoseconds is no use. The easiest way to gain lifetime in order to drive catalysis is to apply a voltage to get fields at that interface which separate charge. And when you apply a field, the lifetime goes up, and eventually you see a rather distinct decay phase here, which is holes stuck at the surface of the hematite, which are waiting at the surface to oxidize water. And you can see the timescale of water oxidation is the timescale of seconds in this case on hematite. And so we have this large kinetic challenge, and indeed that large kinetic challenge, just as in PS2, comes at an energy cost. In PS2, there's this cascade of energies going down. Here, you apply a voltage in order to, which is an energy input, in order to gain that lifetime. Of course, there's other ways of gaining lifetime. Lydia, I'm sure, will be talking about some of the surface functionalizations you can do on these oxides to make junction to separate charge. I'm not going to touch that today. I'm just going to talk about what happens on to these holes at the surface. And so we have the idea that you're going to accumulate holes at the surface that are going to drive water oxidation. I'm interested in the timescale of reaction. And one of the things that really interests me is that the valence band holes in some of these oxides are very deep. And when you think about what are the different ways you can oxidize water, then of course the simplest concept is you have a concerted 4-hole reaction, just as we do with PS2, which enables us to oxidize water to rather small overpotential. But of course you also can oxidize water by a 1-hole oxidation to the hydroxyl radical, and that's much deeper. But of course, energetically not so far off what some of these oxides could do. And it's interesting to try and understand what's going on. Most people trying to understand mechanism tend to try and look at identify the intermediate states in the catalysis. Our work doesn't do that. Our work is simply going to be looking at what are the timescales of these holes reacting to make water, and the holes on the surface of hematite is typically thought of as an iron 4 oxo group. So we're going to be measuring the spectra, the absorbance of those iron 4 oxos, and trying to understand as we change the density of charges at the surface, how does the rates of reaction change? It actually turns out to be rather simple. So this is an optical measurement of the density of these holes at the surface. This is the current. If you plot the density of the holes versus the current, you get a plot like this. This is some work we published a couple of years ago, which showed that at low hole densities at the surface, you have a simple first-order reaction. So essentially all the holes are operating independently to oxidize water. At higher carrier densities, you move to a third-order behavior, where the flux of water oxidation goes up as the cube of the of the whole density. At the time, that rather surprised us. We might have imagined it to be fourth order because there's 4 holes to oxidize water, but we observe a third order behavior. And indeed, we did a whole bunch of different measurements to confirm that the order of reaction changed from first order to third order as you change the surface density of the holes. It's interesting to think about what what that density of holes really is. It's the order of about 1 per square nanometer. So it's the order of about 10 to 20% of all the surface metals are oxidized, which is a very high density. People tend to talk about catalysis as being at defect sites on oxide surfaces. Defect sites on oxide surfaces are much lower charge densities, much lower densities than these densities of charges we're talking about. And so we're more interested actually in the water oxidation just on the rather straightforward surface of these oxides. And the fact that we observed two reactions, one first, one third order, suggests two mechanisms. The first order reaction most obviously is what I mentioned, it's the direct oxidation of hydroxyl radical. That's rather unexciting. It's not very fast because it's got an activation barrier, because it's energetically unfavourable. And what's more interesting is how this third order reaction happens. So that's what I'm going to talk about for the rest of today, before I get on to the electrocatalysts.
The rest of the day.
Rest of my talk today. My talk today. Sorry. So,
day lasts 10 minutes.
Am I doing? Yes, that's fine. So, this is a plot which plots that surface hole density versus the turnover frequency of the holes. If you were to talk about the turnover frequency of water oxidation, it would be 4 times slower, because there's obviously 1 oxygen per 4 hole. But you have the idea that the turnover frequency starts off being independent of hole density, because that's just for 1 hole oxidation, and then it accelerates. And you can see the turnover frequency depends upon how many holes are at the surface and which oxide you use. It goes from something like a tenth for hematite at low hole densities up to almost 100 for tungsten oxide at high hole densities. There's a trend that the deeper the valence band, then the faster the kinetics, which is what you might expect. We'll come back to that a little bit more. One of the interesting things here is how we think about it. But of course, these holes are not the catalytic states. There must be catalytic states which are doing the water oxidation. And what we believe is going on, and essentially the picture we think of, is that there's an equilibrium between the holes we generate and the catalytic states which we're trying to drive towards water oxidation. And particularly, of course, the rate determining step, which, if it's a third order reaction, must involve 3 oxidations. And so essentially the way we think about it is that we have some sort of catalytic rate determining step which has 3 oxidations within it. And then we have these holes at the surface. And the more holes you have, the more you drive the equilibrium towards that catalytic state which drives the water oxidation. And therefore, the turnover frequency goes up and the reaction proceeds. Slightly different way of thinking about water oxidation than in PS2. Now, because we are measuring timescales and rate constants, then we can go on and directly measure the reaction entropies for the Arrhenius analysis of what's the free energy, of what's the Arrhenius energy, so not free energy, for that reaction. And that's quite interesting. It turns out to be quite rare to measure activation energies for electrochemical processes, but because we're not measuring a rate but a rate constant, we can do it quite easily. And what we observe when we do that temperature dependence is that the first order process is activated. It has an activation energy of 300 millivolt electron volts, or 7 kilocalories per mole in the language of catalysis. But what was really striking to us was that the third order process, the one which is the dominating one under solar conditions, is almost activationless. The activation barrier is 1.5 kilocalories per mole. Much less than PS2, which seems quite striking to us. And in a very simple sense, is indicating that hematite does indeed catalyze the reaction of water oxidation because it's lowering the activation barrier to a reaction. And that seems to us to be interesting. So immediately this opens up questions of how you can have a reaction path with such a low activation barrier. Before thinking about that, we've done other measurements, which are the typical sort of measurements you can do to probe catalysis, to probe mechanism. So we've done pH dependencies. We observe the third order reaction is rather pH dependent, independent at low pH. When you go above the PZC of hematite, which means when you start to deprotonate the surface, the rate constant goes up. We suspect that's related to the idea that if you deprotonate the surface OH groups, then you turn on proton transport pathways on the surface of the hematite, which allows protons to move away from the catalytic site and help to stabilize, to help do the redox leveling, which we know is so important in PS2. We also can do kinetic isotope effects. This is a hydrogen deuterium exchange. We get a number of about 1.6 for the kinetic isotope effect for the third order reaction. That's actually, again, rather similar to PS2. And it suggests that the water oxidation, the rate determining step, doesn't involve breaking an OH bond. which is interesting in terms of mechanism. We spent a long time trying to puzzle over what that all meant in terms of mechanism, we linked up with Victor Batista, who of course was talking to us yesterday. The day before yesterday? Maybe day before yesterday. About what might be a possible reaction path which enabled water oxidation with those observations of pH independence, a small Cocatalyzed effect, and a very small activation barrier. And after many calculations, this is and discussions, this is the pathway which seems to make most sense to us in terms of that reaction mechanism, where essentially we have we start off with oxidizing. The model he used was a simple dimer model. You oxidize a dimer twice to make two neighboring iron 4 oxos, and then the third oxidation turns out that if you have two iron 4 oxos, they would typically have some sort of surface bound water. These two holes would put electron density away from that water, enabling that to get oxidized. And so the third oxidation forms this hydroxyl radical of the surface, which then goes on to form the peroxide bond here. And the activation barrier comes from OO bond formation, as you might expect. And indeed, in those calculations, the activation barrier is rather small. What you can see here is also interesting, is that each of these steps of oxidation are essentially at the same energy. In other words, we have redox leveling happening in that system, and so that the third oxidation is more or less the same potential as the first oxidation.
You have a nucleophilic attack there.
You could say, you can call it nucleophilic attack, Jim, if you would, yes. Though of course it's pH independent because the water's bound to the surface. Sorry? It could have been overcoupling. It seems not to be in this case. Indeed. I'm not going to get into the discussions of PS2 about so this is a simpler picture of that mechanism. The idea we can see a peroxide is consistent with several mechanisms proposed in the literature. The rate determining step seems to be inconsistent with all the data we have. And the reason why the rate constant is slow is because of equilibria. It's because most of the time the charges are moving around at the surface, and you have to have three of those holes coming together to populate the rate determining step to drive the water oxidation. And probably when we shift the valence band energy of the oxide, that's simply shifting this equilibrium more towards the rate determining step. Another way of thinking about that, of course, is if the holes move around on the surface, have a high degree of entropy because there's many holes on the surface. And as you move towards the rate determining step, then you lose entropy. But of course, as you increase the hole density, then those entropies change and you drive the equilibrium towards the right-hand side, which why the rate accelerates as you increase the hole density. And the idea, of course, is something which is very much in parallel with what we have in PS2, that the oxidations of those surface holes pulls electron density away from an oxygen, which allows that to get oxidized in a later step to form the radical, which then drives the reaction. The only difference here is that in PS2, if we follow Jim's model of a nucleophilic attack, which I'm not going to go into, but anyway, if we did, then that's got two metal-bound oxygens involved in the reaction. On hematite, the two metal-bound oxygens are too far apart to directly form an OO bond, which is why you need the surface oxygen between those two bridging oxygens in order to drive the OO bond formation. So just at the end, I'll finish by talking about not a photo-driven reaction, but an electro-driven reaction. And many people suspect that if you want to split water with light, probably PV plus electrolysis may be a more attractive way to go than direct sunlight, but that's an interesting discussion. And we've done some work looking at some iron and nickel oxyhydroxide systems, which is one of the most widely studied electrocatalysts for water oxidation. Well, we're going to do the same thing. We're going to track the population of carriers optically, in this case not with light to drive them, but with voltage driving the reaction. Now, one of the biggest differences here is that when you try and oxidize hematite, that's a semiconductor with a band gap and a valence band and a conduction band. And so you know that in the dark there's no holes in the system, and you can generate the holes with light and bias. Most electrocatalysts like this, they don't have a single oxidation state. They're not a semiconductor. So essentially you have a distribution of redox states, and you gradually oxidize that system. And typically, what we observe is different redox couples which can be oxidized in trying to drive water oxidation. So in this case, for example, typically there's two couples, the iron 2, iron 3, and the iron 3, iron 4. With nickel, it's different. And you have to understand not just how many holes, oxidations you have in your system, but for how many holes you have for each of these redox waves. And so we have to measure the densities of the iron 3 and the iron 4 and the iron 2 in the system in order to make some sense of a rate law analysis. Often people talk about this being the precatalytic wave and that the catalytic wave. Because we have optical spectroscopy, and we can, those states can be distinguished by their optical colour. And so, for example, so these are the spectra of the precatalytic state oxidations. So technically that's the absorption change associated with going from the iron 2 to the iron 3, and from the iron 3 to the iron 4, and the equivalence for the nickel system. And so we're able to separately track the two different oxidations which occur in those electrocatalysts as you follow as a function of voltage. And then we're able to track that against the catalysis. And of course, this wave of oxidations happens before the current turns on. This wave happens when the current turns on. And what we can then observe is that, indeed, if we just track the second oxidation, so the catalytic oxidation, the state which is driving the water oxidation at the surface, then we can again measure turnover frequencies, in this case versus voltage. You can also plot it versus charge density. And you can see that as you increase the voltage, then the turnover frequency goes up for just the same reason as on hematite. But as you start to increase the density of those holes which are going to drive the reaction, then you shift the equilibrium towards the rate determining step of the reaction. When we measure the rate law, it turns out that for these electrocatalysts, the water oxidation is fourth order in the second oxidation, which was interesting to us. It's different to the hematite system. And you can see the reactions there, the time constants vary between the oxides. I won't go into that. But we think that's quite interesting. We have the same idea, but as you apply a voltage, you just shift in equilibria. You're increasing the density. It's not fully oxidized. The system hasn't gone all from iron 3 to iron 4. It's partially those iron 4s. Those iron 4s move around on the surface. Sometimes they bump into each other. When they bump into each other, if you get four of them bumping into each other simultaneously, then you reach the rate determining step, and then you can drive the reaction. We haven't yet done all the pH dependencies and things like this to try and understand better the mechanism. So we're still at another, that's the level of our model of water oxidation on the system. Of course, there's other studies in literature on the model. I won't go into that. One of the interesting things, of course, here is that this only works if you have redox leveling. It only works if the rate determining step is not energetically way above those holes at the surface. And so for this really to work and to see such behaviour, then I think we have to have the same sort of redox levelling as we have in PS2. And I think that has to be one of the keys to why all these systems work for water oxidation. So I'll finish just with some conclusions and thoughts that just as with PS2, water oxidation on photoanodes has the same issue. You've got to match lifetimes, and that's cost energy. And of course, in general, if you want to improve efficiency, it's all about trying to gain lifetime with a minimum loss of energy. There's a difference in how we think about the ratcheting up of oxidation at the surface. But with PS2, we have the idea you ratchet up through the S states to oxidize water on photoelectrodes. Then what's more obvious is that you increase the density of surface holes, which gradually shifts the equilibrium towards the rate determining step. Similar to PS2, these materials seem to exhibit some sort of redox levelling, which is almost certainly associated with the idea that when you oxidize them, then you have the oxidized hole deprotonates on the surface, and that means that that when you try and bring two holes together, there's no Coulomb repulsion, which is why it's feasible to bring multiple holes together to drive a water oxidation. We have some evidence that the idea of proton transfer pathways to get holes away from the surface may be important. If you start to deprotonate some of the OH groups on the surface, they will provide pathways to protons to get away from the surface more quickly, and that may be why the rate accelerates at more alkali pHs. And we see kinetic isotope effect and pH effects, which are similar to PS2, according to the measurements which Gary has. We have some differences, and so on hematite, The rate determining step is third order, while I think with PS2 you would think this is the fourth oxidation, which is for rate determining step. And the activation barrier for hematite is actually lower than for PS2. Though, of course, that's slightly cheating because the valence band is so deep, it's able to access states which from PS2 you couldn't access. You couldn't oxidize a surface bound water in PS2 because the hydroxyl radical would be too energetic to form in that system. With PS2, with hematite, the energy is deeper, and so you could drive that reaction. On electrocatalysts, where the energetics are not as strong as on hematite, then you can't oxidize a surface water, because again, that would be too hard. So almost certainly, it's a reaction mechanism which maybe is closer to what we see in PS2 and some of these molecular catalysts, where we were oxidizing directly metal-bound oxygens and driving water oxidation that way, which maybe is why the electrocatalyst behaves as a fourth-order process rather than a third-order process. With that, I must thank everyone who's been involved in the group, particularly my own guys, Camillo, Florian, Elia, and also Sasha and Shababa, and all the people who we've collaborated with, and particularly, of course, for those calculations to Victor. Thank you.
Thanks, James.
Hi, James. I'd like to ask you, if I understood properly, you increase the lifetime of your holes on hematite using an anodic bias. And I was wondering, what is the potential you need to increase this lifetime, and if you find a correlation between bias and time on lifetime?
Absolutely, you need to, so we apply a bias essentially to remove electrons from a surface so that the whole lifetime can be longer. Essentially, we suck electrons away in a depletion layer. In general, there's a correlation between the lifetime of the holes and the bias. The stronger the bias, on average, the longer lifetime. Though actually, once the holes are at the surface, as long as you can turn off the recombination pathways, then the lifetime becomes entirely controlled by the water oxidation and independent of bias.
But what is the absolute potential you're applying?
It's typically about a volt. But it depends on what lifetime gain you need. So hematite has a large kinetic challenge. You have to apply a large voltage. Titania has a smaller kinetic challenge because the water oxidation is faster and the carrier lifetime is shorter, and the voltage you have to apply is much less. And so it depends on, essentially, there's a direct correlation between the amount of lifetime you have to gain and the amount of voltage you have to apply. So.
Well, this is extremely interesting and entirely new to me, so forgive my question. In a quite different field, higher order reactions, for example, third order reactions, are very common. But in essentially every case, but one very special case, in essentially every case, the way the third order reaction occurs is that two of the particles come together, survive for a while, and then the third one comes in. So my question is then, in the case of these third and fourth order hole reactions, is that the situation here? In other words, two holes come together, form a species, which is an equilibrium of the holes, then a third one comes, equilibrium, finally your fourth order, etc.
Yes, that's exactly the model. And so the picture I have here is the idea you have separate holes, two of them come together side by side, and what you have to then hope is that before they fall apart again, a third hole comes along. And the third hole then doesn't oxidize one of these ions. Again, it oxidizes for surface water.
Very good.
That's how we think. It's only a proposal, but it seems to make sense to us.
Thank you.
Jim, if you put water oxidation catalyst on the surface, let's say hematite,
yes.
What is the minimum requirement in terms of turnover frequency for the catalyst, considering the kinetics, the charge transport sometimes becomes a rate determined step?
So I avoided talking about that because it's quite a complicated story, but on one level, so the data I showed on those iron and nickel hydroxide, oxide electrocatalysts, if you put those onto bismuth to make a photoelectrode, where those are now a co-catalyst, you get exactly the same kinetics. Because so a co-catalyst behaves the same way as an electrocatalyst on the surface.
So the Cocatalyst efficiency in terms of tenor frequency does not play any role at all, right?
So then you have to ask the question, why do you want to have a catalyst there?
Yeah.
And one of the interesting things, if you look at timescales, that, for example, we've done a lot of work on cobalt oxide, Copy as it's called. There, the turnover frequencies are of the order of 0.01 per second, slower than hematite or titania. And so, in that case, you put the catalyst on and you slow down water oxidation in that sense. And so, in that sense, that material, its catalytic properties are actually rather unimportant. It works because it makes a junction which helps separate the charge. It's interesting on one level, these timescales of water oxidation are already fast enough because they're able to oxidize water. 1 per second isn't too bad. I think what's most interesting is that the electrocatalyst I showed were oxidizing water at a much smaller overpotential than hematite. Because hematite's Venice band is very deep. The iron-nickel systems are able to oxidize water with much less overpotential at the same time scale. And that becomes interesting if you want to go to semiconductor materials which have valence bands which are not deep enough to oxidize water usefully without catalysis. And then I think it's interesting to add a catalyst. And so, to me, it's interesting to make junctions. That's good. Junctions will help separate charge. But if you really want to accelerate catalysis, that's most useful when you find that the catalytic timescale is really limiting for the material. And that will be for materials which are unable to oxidize water without a catalytic surface.
Okay, thank you.
Is that okay?
Yeah. Thanks, Prof. Since you are just talking about CoPI,
yes.
So in your previous paper, I think it's Yimen did the work.
Yes.
Yeah. So Yimen, you found that the CoPI is plays a role in retarding the black hole and electron recombination.
Yes.
And then you're talking about electrocatalyst, catalyst.
Yes.
So it's in another perspective, the kinetics. So what if you apply nickel oxide hydroxide on bismuth vanadate or on hematite? That would it play a same role of retarding the back electron and hole recombination, or it have bifunctional bifunctions?
Yeah, I think you should give my talk. That's very good. It depends on the details of the kinetics. And so if we put, we've done the work, I haven't yet published it, we've written it up, but if you put the iron oxy hydroxide systems onto bismuth vanadate, then on a flat surface it doesn't make much difference because the timescales of water oxidation, it helps slow down recombination, but catalysis doesn't accelerate. If you go to mesoporous systems, where you have a big problem with how to accumulate charge at the surface because the particles are so small, then the electrocatalyst is absolutely critical because it enables you to separate the charge onto that catalyst and then still drive water oxidation where you separate the charge going downhill because the holes move to the electrocatalyst. So you have to understand the details of the kinetics to know when it's useful to put a catalyst on the surface.
What if before microstructure?
Last question.
Yeah, James. I was wondering about why you propose the surface water forms a radical and not one of the bound oxos, basically. Could you repeat that argument?
Of course you could, but on hematite, the bound oxos are too far apart to form an OO bond, at least on the surface which is the dominating surface of water oxidation. And so that wouldn't help you in terms of water oxidation. Which is why, as far as I understand from Victor's arguments, the only way we're going to form an OO bond is if we oxidize a surface-bound water rather than those iron oxos. So, does that make sense? I hope it makes sense.